In this section, we'll talk about important ways to improve machine learning models. So here's the outline of the module. We'll talk about feature selection and regularization. And then afterward, we'll talk about how to interpret features, sweeping model parameters, and cross-validation. So let us start with feature selection. Now, I hope you recall the principle of Occam's razor, which is that the best models are simple models that fit the data well. And because if the models are not simple, there's a good chance that they won't generalize well to new data. So we need some kind of balance between accuracy of the models and their simplicity in order to thwart the curse of dimensionality. So let's go back to our running example where each manhole is represented by a vector of numbers. Do we really need all of these numbers to predict whether the manhole is going to explode? Maybe we can create a simpler model with much fewer numbers, and that would be helpful for many reasons. And first of all, simpler models tend to predict better, as we know from Occam's razor. Simpler models are more interpretable to humans. Also, simpler models are easier to make predictions from. There's much fewer calculations involved, so it's much computationally easier. However, selecting the optimal combination of features is computationally hard. And I put that in blue because it makes people blue to hear that. So myself in my own research, I'm happy to do that computation. We have ways in our lab to do optimal or close to optimal feature selection, but those are computationally intensive methods, and they're not the first thing I want to teach you guys. So let me show you some of the standard ways that people fiddle with the features to try to reduce the number of them that you're going to use. So the first method is called greedy backward selection. So you start with all features, and then you find the feature that hurts predictive power the least when removed, and you simply remove it. You just keep going, and you stop when some criterion is met. Now, it's called greedy because once you remove something, you never look back. You could easily remove an important feature early on, and then there's nothing you can do to get it back. But it is computationally easy. And here, you want to stop removing features when it's actually starting to hurt you, your accuracy, to keep removing them. Okay, so you start here with all the features, and then you remove one that isn't very important for predicting the label, and you keep doing that until you start losing lots of accuracy, and then you stop. And that's how it works. Now, greedy forward selection is a different method. It's sort of like the converse of greedy backward selection. You start with no features this time, and then you find the feature that acting by itself is the best model. And then you keep that feature, and then you add another feature so that the combination of the two is the best. And you keep those two, and then you add another one. And you keep going, and you stop when some criterion is met. So it's called greedy, again, because you never look back. So what if you chose to include a feature near the very beginning of this procedure that in combination wasn't really that useful? You can't get rid of it. You're stuck with it. On the other hand, it's definitely computationally easier because you never look back. And so usually you stop here when predictive power stops increasing very much and you get diminishing returns for each feature that you add in. Okay, so you start from nothing, and then you add in one feature at a time, like that. And you never end up looking at the rest of the features, right? You realize that you've reached a point of diminishing returns at some point, and that's where you stop. Any feature you choose to add would make the model more complex, but it wouldn't really get you very much more accuracy, and that's where you stop. Now, in order to do this method, you have to choose two things. And one of them is the criteria you're going to use to choose which feature to add next. Now, the simplest way to figure out which feature to add is to choose one that gives the largest boost in accuracy. I'll talk more about that in a few minutes. And the other criteria is when to stop. And again, that's when you reach the point of diminishing returns. So how do you know when to stop? So how do you know when you reach that point of diminishing returns? And that's where something like adjusted R-squared comes in. I hope you remember R-squared from the data science course. R-squared is a measure of how well the model fits the data. So if the model and the data are always close together, then y and f are close. Their difference is small, and then this whole thing is small, and this whole thing is close to 0, and then r squared is then close to 1. Okay, so r squared measures goodness of fit. And then the denominator here doesn't depend on the model. It's just a property of the data, so it has no opinion about the model. Now, adjusted r squared has the r squared in it, but it has also a penalty for how many terms are in the model. So if there's p terms in the model, this is the penalty. So this thing doesn't just like accurate models, it also likes sparse models. So let's discuss this a little bit further. So let's say that you have a ton of terms in the model, like a ton of them. Then p is really, really large. And then I'm claiming that the adjusted r squared will not like that. Okay, so if p is big, what happens? Then this ratio is big, and then you're subtracting something that's big. And so this whole thing is, so this is small, okay? Now that's cool, because it says if you have too many variables, your adjusted r squared is small. It's not good, even if your r squared is good. So what if p is small? Well, in that case, you're only subtracting something small from r squared. So that's good. But then since you only used a few variables, then your r squared in the first place might be terrible. So again, there's a trade-off. And what you want is something that's just right? You want enough variables to have your r squared be large, but not so many that it's going to bring your adjusted r squared down. Okay, so let's plot what happens when we do forward selection. I'm going to plot what I think will happen to adjusted r squared when we do this greedy forward selection. The model's going to start with one feature, and then the adjusted r squared is going to go up as the gains in r squared are better than the loss for having more features in the model. And then it goes up, and just at the top, when you think everything is going well, you add too many features, and then the gains in r squared are not as good as the hit you took for adding more features so the adjusted r squared goes down. But you found out where the sweet spot was. It's right here. And now you can use just that many features. So r squared here told you when to stop with the forward greedy selection scheme. Okay, so that's the idea.